Hello friends and welcome at my channel. Today let's talk about Arcus tangent and its derivative. So this is a kind of familiar situation that we've done in the last two videos. So we have f of x, which is defined as tangent of x, and if I write it the way you're supposed to be writing it at the university, this is f, which is defined as from minus pi divided by 2 to pi divided by 2, and we are going from minus to plus infinity, right? So if you remember the graph of the tangent, so one of the branches of the graph looks like that. So we start here, end up there. So this is minus pi divided by 2, and this is pi divided by 2. And of course, the graph isn't defined neither at minus pi divided by 2 nor at pi divided by 2 because we would be dividing by 0. So what is the inverse? The inverse is, of course, so we write here x is going to the tangent, that's clear. And the inverse is, well, reverting the process. So we are coming from minus to plus infinity, and we're mapping it onto minus pi divided by 2 to pi divided by 2. So let's see how the graph would look like. Okay, so tangent of 0 is 0. So Arcus tangent of 0 is 0 as well. Then we have two asymptotes. This is the first one at pi divided by 2, and this is the second one at minus pi divided by 2. And let's see what's happening. Well, we are approaching pi divided by 2 the same way with the Arcus tangent, the same way the tangent is approaching plus and minus infinity. Also, tangent of pi divided by 4, if you remember that, tangent of pi divided by 4, the kind of famous value because it's 45 degrees, and this is exactly where the slope is equal to 1. So it's really equal to 1. So that means the Arcus tangent of 1 is pi divided by 4, so exactly in the middle. All right, so somewhere here. And the same, because we're symmetric considering the origin, we're also here. And we can compute further values if we like it. And then we will see pi divided by 3, pi divided by 6, and you will see it's such a graph. Okay, so the easiest way to figure out how the graph looks like is just to produce a table to compute the values, and then you connect the dots. All right, so once again we see no troubles considering the differentiability of the function. It seems to be, well, everywhere smoothly going. That means we can put in a tangent line everywhere, and well, let's go for it. So what is the derivative of the Arcus tangent? So Arcus tangent prime at tangent of x is equal to 1 divided over tangent prime of x, right? So this is the way it's supposed to be working. And now maybe you remember there were two different ways how we can write down the derivative of the tangent. The first one was it's 1 divided by the cosine squared of x, which is fine, but not necessarily what we need here because there is a better one. And this is 1 plus tangent squared of x. And now you see maybe why this one is better. Well, the thing is, if we are plugging in the second one, then we already are dealing with the tangent. If you look at the last two videos, previous two videos with sine and Arcus cosine, I had to kind of play with sine and cosine. It had to substitute them in order to end up with sine and cosine correspondingly. Here I don't have to do it. I can just immediately replace, as you can see right there in the next step. We're having 1 divided over 1 plus tangent squared. And this is nice because we already done. Why is it the case? Well, arctan prime at tan of x equals to 1 divided over 1 plus tan squared, right? So that means if we are replacing tan by z, let's put it this way, what would we have? Well, you see it's arctan prime of z equals to 1 divided over 1 plus d squared. And we're done. Thanks for watching. See you in the next video. Bye bye.